All right. Hey, everyone. I hope you're excited. Last talk of the day. So, my name is Sabrina Volponi. I just finished my PhD at the University of Notre Dame, and my research interests lie in exploring the intersection between ecology and fluid mechanics. For my PhD, I studied transport in streams, fracture networks, and colloidal systems. And I just accepted a postdoc at Washington State University, where I'm really going to focus in on streams. Streams are going to be the subject of our talk today, specifically how biofilm development, senescence, which is a fancy word for death and decay, and substrate type, the rocks at the bottom of the stream, influence hyporheic exchange. By the end of this talk, I'm hoping you'll walk away with a basic understanding of how transport in rivers works, an understanding of how the physical and biological composition of a stream impacts transport, and you'll walk away with tools for identifying these effects in breakthrough curves yourself. With that, let's take it from the top. So we can think about streams and rivers as essentially being the gutters of a watershed, taking material that comes in and transporting it to oceans, lakes, and other rivers, among other water bodies. Among the material that comes into streams can be contaminants. Things like bacteria, which can come from inadequately treated wastewater and pasture runoff, heavy metals, from mining operations and landfill leachates, and nutrients, which can come from agricultural runoff and lead to the development of harmful algal blooms. Now, maintaining the health and integrity and usability of our streams, rivers, and other waterways is integrally related to our ability to model transport in these systems. But hey, we've been here for almost 2 weeks now, and at the very beginning of this, Tomas showed us how to use the advection dispersion equation to model transport in our systems. So cool beans, we're armed with the tools we need. So using this equation, you can make predictions as to how concentration on the y-axis changes with time, producing a plot known as a breakthrough curve, like this. Well, then you go to a stream, and you collect concentration versus time data, and you end up with a profile that looks more like this. Notice, while the advection dispersion equation does a great job of matching concentrations at the peak, it performs less well catching these low concentration regions that we call a tail. Now, differences between the advection dispersion equation and a real breakthrough curve that you'd measure in a stream or river can differ in the tails by up to 10 orders of magnitude, meaning that the actual concentrations in our streams and rivers can be 10 billion times greater than the amount that's being predicted by our models. So, why do we care? Well, first, if we're monitoring the transport of something highly toxic, like heavy metals, even a small misrepresentation of the actual concentration can be pretty severe. Secondly, let's go back to the lecture from Dr. Audrey Sawyer this morning. Remember, reaction and degradation relate to how long material is being stored in the stream. And this tailing behavior relates to material that's being stored in our system the longest, so has the greatest potential for secondary reaction or degradation. So okay, I hope I have you convinced at this point that there is a pretty big mismatch. So what's going wrong here? Well, to get at this, let's conceptualize transport in our stream. Imagine a solute traveling through a river. It's going to go back and forth between traveling through the main channel, a region with unrestricted fluid flow, and the subsurface, the region at or below the rocks at the bottom of the stream, where fluid velocities tend to be much slower. So why is it slower? Well, first off, we have rocks. Rocks have smaller interstitial spaces, which slows down fluid velocities. Secondly, we have biofilms. Biofilms are collections of microorganisms that excrete an extracellular matrix. More simply put, if you've ever reached your hand into a stream and pulled out a rock that was kind of green and slimy, that green slimy thing is a biofilm. Traveling materials can interact with the biofilms and be either held and retained, slowing them down, or depending on the solute that we're monitoring, they can be degraded. So these are two things, the rocks and the biofilm, that have the potential to slow down transport. To look at this more quantitatively, 2 studies were conducted using a set of artificial streams at the University of Notre Dame. And they were looking to see whether the types of rocks lining the bottom of the stream and whether biofilm accumulation produced a noticeable impact on transport. Now, Abena et al. Came first in 2016, and they found that the substrate exerts a primary effect on transport, but biofilm growth could homogenize transport behaviors between streams with different substrates. Cool. A few years later, Roche et al. Came back, used the same set of streams, and couldn't identify neither a biofilm nor a substrate effect. So, how is it possible that two experiments conducted in the same streams got different outcomes? Well, that's going to be the topic of our talk today. Before we get too deep into it, we first have to ask ourselves, is it even possible that we can recreate a breakthrough curve? If breakthrough curves couldn't be reproduced, it might suggest that differences between studies were due to the stochastic nature of transport, as opposed to real differences due to substrate or biofilm. To explore this question, we conducted a series of replicated releases using the artificial stream facility at the University of Notre Dame. We used 4 streams that were engineered to be identical replicates. They were concrete lined and filled with a mixed substrate of equal proportion sand, pea gravel, and cobble. In each stream, we conducted 2 to 3 consecutive Rhodamine-WT dye releases. Rhodamine-WT is really cool because once you inject it, it turns the water this bright pink color. We can then measure changes in the concentration of this dye over time at a point 50 meters downstream using a sonde. Between each release, we waited 4 hours for concentrations to return to pre-release baselines. Here's what we found. Okay, on the plot behind me, we've got concentration on the Y, time on the X. Color indicates the individual stream that a release was conducted in, and shape is going to tell us the replicate release number. Let's look at some curves. Okay, first thing that I want you to see here is that these curves look pretty similar. It's especially true if we put this on a linear axis like this. If we want to go further than the eyeball test, we ran a quantitative statistical analysis called the Anderson-Darling test. What this test is designed to do is assess whether multiple PDFs are just different samplings of the same overarching parent distribution. More simply put, it's a statistical test that says, can we say with some degree of confidence whether these curves are the same or different? The statistical test showed us that these curves are pretty much the same. We couldn't find a significant difference. Okay, here's why this is cool. We've got 4 streams with an unknown distribution of subsurface features that slow down transport. And in each release, we're finding that we're sampling a same distribution of immobilizing residence times. So, this suggests to us that as long as subsurface conditions remain constant, we should be able to reproduce a breakthrough curve. Pretty cool. Okay, let's bring this back now to the 2 experiments that we started with. By design, we know that the physical streams that they were conducted in didn't change. So if they're physically the same, the difference might have to do with biology. To better explore this idea, we conducted a series of natural variation experiments in 4 streams at the artificial stream facility at Notre Dame. We used 4 streams with different substrates, the smallest being sand, then pea gravel, cobble being the largest, and then a mixed treatment of equal parts of all 3. We controlled biofilm growth using light exposure. At the beginning of a 12-week period, we covered all of our streams with a shade cloth, designed to block 90% of the photosynthetically active radiation. We left the shade cloth on for 3 weeks, removed it, and conducted our first set of releases, the shaded treatment. We then left the streams in the sun for 3 weeks and conducted the next set of releases, early development, waited 3 more weeks, did the next set of releases, late development, and then recovered everything with a shade cloth, blocking light, letting the photosynthetic biofilm die. We then removed the shade cloth and conducted our last set of releases, reshade. We did this whole procedure twice in 2020 and 2021, producing a total of 32 breakthrough curves. Here's what we found. Okay, so here again, we've got concentration on the Y, time on the X. The columns give substrate, and the rows give our different biofilm treatments. Color is then going to give us the 2 years that we conducted releases in, 2020 and 2021. Here we go. Okay, that's a lot of data all at once. What I want you to see is that within a given substrate and biofilm treatment, we saw significantly different breakthrough curves here, and here, and here, and here, and here, and here, and here. 7 of the 16 pairings showed significant differences between 2020 and 2021. which is pretty big. Coming back to what we started with, we know that the streams remained physically unchanged because that was our experimental design. And if subsurface conditions were constant, we know we should have been able to reproduce these breakthrough curves. So it wasn't the physics that changed, it had to be the biology. To explore the effects of biofilm a little more specifically, let's rearrange some of these pairings. Here now we still have substrate in the columns, but the rows are going to give us our year. Let's compare our shaded to our reshaded treatment. Now these treatments are similar in that they were both conducted after having been covered by the shade cloth. So we expect all of the photosynthetic biofilm would have died, and so this community should have consisted mostly of senescing or decaying biofilm and heterotrophs that were hanging around to break them down. Okay, data time. Oh, right, and the difference between this, so they have a similar community composition. I'm going to re-hide that. What's different and why we're comparing them is related to the amount of biomass. The shaded treatment coming at the very beginning of the field season should have had a much lower biofilm community, a much smaller biofilm community. The reshaded treatment coming at the ends of the field season had a whole summer to build up their biomass. So what we're going to compare here is just how does the amount of biomass impact transport. Okay, now I'm ready to show you data. Here we go. What I want you to notice is that there are significant differences between breakthrough curves in all of these. 5 out of the 8 pairings displayed significantly different breakthrough curve shapes between shaded and the reshaded treatment, which suggests to us that the amount of biomass impacts transport. Okay, so what is the biofilm doing that's causing a transport effect? Here we're just looking at the little bodies that are hanging around with no real biological function. So is it just that having biofilm increases structural heterogeneity that's affecting transport? Or is there something more? Is there something related to the living component of biofilm? We saw in Pietro D'Anna's talk that biofilm can modify its architecture to try to maximize nutrient exchange with its surroundings. We've seen something pretty similar in student posters if you walk around. So maybe there's a living factor that's at play here. To explore this, let's look one more time. We're going to compare the late development to the reshaded treatment. Now, coming one after the other, we expect that these two treatments will have a similar amount of biomass, a similar number of biofilms, if you were to count things. But the reshaded treatment, coming after the application of the shade cloth, we expect to be mostly senescing bacteria. Meanwhile, the late development treatment should have a whole lot of photosynthetic individuals that are using the sunlight to stimulate growth. To compare the amount of living biofilm between the late and reshaded treatment, we compared the amount of chlorophyll A, which is a proxy. Chlorophyll A shows the amount of green photosynthetic pigment that's used for photosynthesis. There are 2 treatments where we could show a significant difference in the amount of chlorophyll A between the late and the reshaded. I'm going to show you the breakthrough curves for those 2 where we could really show a difference. In both cases where we know we had way more chlorophyll A in the late development than the reshaded, we see significantly different breakthrough curve shapes. What this suggests to us is that the living component of the biofilm, in addition to just the structural heterogeneity that's caused by having their bodies present, is influencing transport. But let's try to take it a little further than this. We've related our breakthrough curves to in-stream transport parameters using the Stochastic Mobile Immobile model. What I want you to know about this model for the context of this talk is that it does a better job of capturing the tailing in our experimental breakthrough curves than the traditional ADE does. By fitting the model to our data, we can determine values for 4 different in-stream transport parameters: the mean velocity and dispersion of traveling solute, exchange rate, which refers to the frequency with which material drops into the subsurface, and power law slope, which is a measure of how long material is retained within the rocks at the bottom of the stream. We then looked to see whether we could relate any of those in-stream transport parameters to trends in our biofilm. Specifically, we looked at chlorophyll A, which is a proxy for how much photosynthetic life we have growing. Using a regression tree analysis, which I'm going to show you here, what we saw was a significant nonlinear relationship between chlorophyll A and in-stream velocity, where there's a threshold, above and below which we see faster and slower velocities. We can define this relationship more explicitly using a general additive model, which looks at how chlorophyll A and velocity relate nonlinearly with this red line. What I want you to see is that as chlorophyll A, or biofilm, begins to grow in our system, velocity decreases. We think this is happening because chlorophyll A, or the biofilm growing at the benthic surface interface, is increasing surface roughness, causing the flow to slow down. Eventually, though, we hit this critical threshold amount of chlorophyll A, after which velocities begin to increase. What we think is happening here is that the algal mat at the benthic surface interface is getting substantially thick, such that it's smoothing down that roughness signature and allowing flow to speed up. While this all sounds well and good, the other thing I want you to notice is that this model explains about 50% of the deviance in our data. So while it sounds good, this as a predictor on its own isn't the best. So what could do better? Well, maybe substrate. Let's try this again now. Our regression tree analysis suggests that substrate produces a significant driver of trends in velocity. The corresponding GAM analysis shows us that sand supports velocities that are much higher than that of our other substrates. This is likely due to sand being the smoothest substrate that we tested, allowing for faster in-stream flow. The next thing to notice is that our GAM explains about 84% of the deviance in our velocity data. This is pretty cool for a few reasons. First, I can just look at what substrate is in my stream. I don't need any fancy analyses or mathematical models to figure that out. So it suggests that there might just be an easy way to ballpark what a velocity might be. Secondly, anthropogenic activities are leading to sediment runoff into streams and rivers. What this suggests is that there might be a way to predict a priori how human activity is going to change velocities in our river. We can make similar conclusions looking at substrate and exchange rate and power loss slope, but this one is by far the best. So if you have questions, I'm happy to take them at the end, but I'm going to skip over it for here. Okay. Let's tie this all back to our original question. How could two scientists conducting releases in the same streams draw different conclusions on the importance of substrate and biofilm? What we suggest is that the problem lies in the analyses that they used. Obana et al. Noticed substrate and biofilm effects by directly comparing breakthrough curves generated between releases. We did the same thing here, and we were able to notice both biofilm and substrate effects on transport. In contrast, Roche et al. Tried to look for linear correlations between in-stream transport parameters, substrates, and biofilms. They couldn't find an effect. What we show here is that this relationship exists, but it's nonlinear, explaining why a linear analysis couldn't draw a substantial conclusion. So, why did they differ? Choice of analyses, which suggests how you go about analyzing your in-stream data matters. Okay, let's tie all of this up with what we learned. First, we showed through replicated releases that as long as subsurface stream properties remain constant, breakthrough curves can be replicated. This is awesome because it means when you're doing tracer studies, you don't need to do 2 or 3 releases. One is enough to get a sense of what's happening. Secondly, the biotic and abiotic, the living and the not living, components of the biofilm both influence transport behaviors. And finally, substrate appears to be a primary driver of velocity trends in streams. It explains the majority of the variance. Biofilm effects matter too, but they're a secondary driver. And with that, that's everything I hope to share today. I really appreciate getting to show my work to all of you, and I'm happy to take questions.
Thank you, Sabrina, for the very nice presentation. Is there any question? Thomas?
So just a quick question, sorry to stop you. I do know the guys with that with the other works that I'm familiar with the streams as well. Especially since they are under pretty controlled conditions, I'm wondering if you could measure these velocities, right? Because in the end, these mobile fits, they work extremely well. It's embarrassing how they work. But it's still not completely obvious if the velocity you're measuring is the exact stream velocity. So could you go and check?
Ooh, I am not sure how to measure the average in-stream velocity. I know the flow rate and like the discharge in the streams.
That's good enough. Have you tried to use just the discharge and the size of the stream? They're pretty well-behaved streams, right? So even something like that, I would like to see.
That's fair, but it wouldn't capture the components of hyporheic exchange that would slow down the flow. It would be an overestimation.
That's exactly my point, right? Like, I'd like to know if this is really an effect on the velocity or if the model is getting confused.
I would have to double check. I believe our flow rates were higher than what we had here. I don't know how significantly higher, but it's worth double checking.
I think we could do that.
Yeah.
Thank you for the very nice talk. I would like to ask about the Stochastic Mobile Immobile model. It's like if you could spend a few more words about it, in particular the parameter that you showed, I guess, if I'm not wrong, related to the rate of mobilization, if you're like setting this parameter in a way to fit with the data, or if you knew already some values for the parameter from other studies.
So how the mobile immobile model works is, let's go back here.
Yeah.
It's essentially an advection dispersion equation that's coupled with a memory function, capturing movement into the subsurface and then how long it's retained there. We're modeling retention in the subsurface using a power law distribution. Beta, the power law slope. Beta is power law slope. It refers to the slope of that power law distribution that's describing how long material is retained in the subsurface. In terms of how we actually got the in-stream parameters, so blue points, this is one example. Blue points are experimental data, orange line is the model. We use an optimization in MATLAB. Oh, it's covered by the bottom, but it's called the SMIM fit library. And what it does is it performs an optimization to try to tune these different transport parameters within physical constraints of our system to best recreate the observed data.
Okay, so it's a mix of physical constraints and
Yes, all,
trying to fit the data.
yeah, as opposed to some upscaled models, what's cool about this one is that every parameter that we're fitting has a physical meaning attached to it. But then it is just an optimization to try to fit parameters to different parts of the curve. Velocity and dispersion are mainly controlled by the peak. Exchange rate is controlled by this, and the slope also relates to power law slope.
Thank you very much.
Yeah.
Okay, you have question? Yeah.
I was just wondering, how do you ensure that there is no chemical interaction when you look at the effect of the biomass in the transport?
Ooh, wait, say that one more time, just a little louder.
How would you ensure in your experimental setup that there is no chemical interaction?
Okay, we use a conservative tracer. To the best of our knowledge, we're monitoring recovery at the bottom by integrating under the breakthrough curve, and we're getting pretty close to unity mass recovery. So we know that we're recovering everything that we're injecting.
Okay. But the delay that you have in the cleaning could be also chemical. I don't know.
No, that's a very good question. It depends on what you're working with. If you were working with something much more reactive, say like EDNA or ARGs, you could see things. In our case, we're working with a conservative tracer, so we know things in the system don't want to keep it forever.
Thank you.
Mm-hmm.
Yeah, statistics-wise, sometimes we can tell two data sets are from different distributions, but the distributions are not different from the sense of physical interpretation. That V might be different by 1,000th of a unit, but just because we have so much data, we can say they're different. when I look at your plots, some of them look really different. And some of them, I bet, did come out with a p-value that said they're different, but maybe the difference was not very physically interesting. When you said that they were different, was that just a p-value, or did you put any thresholds or criteria that, like, well, and that these two velocities are actually of a significantly different value?
Okay, wait. If I can repeat your question to make sure I have this. Are you asking, when I say two curves are different, is it strictly the p-value, or is there some additional criteria?
On, like, the velocities were different by some metric of these would be different. Like if the two velocities were only different by 0.1%, then intuitively you say, well, who cares? But then if the statistics showed that they were just slightly offset, so they were statistically different distributions, it might not be meaningfully different, but it might be statistically different. And I'm wondering, did you add it, when you said they're different, was that purely p-value, or was that also kind of putting some sort of like criteria on what you would see as really different velocities, for example?
I see. So in terms of breakthrough curves, that was exclusively based off of the p-value. We actually ran two tests in playing to try to explore this. There's the Anderson-Darling and the Kolmogorov-Smirnov. The difference between the two is what part of the curve they weight the most in terms of difference. So Anderson-Darling places heavy emphasis on differences in on both tail ends, which for us was a significant thing to pay attention to because the tailing is precisely what we care about. We also looked at the Kolmogorov-Smirnov test, which is much more sensitive to differences in the mean of the PDFs. And generally, the two tests agreed with each other in terms of which curves were the same or different. The in-stream transport parameters are harder to directly compare because we only have one measurement for each. So there's no variation to say, this is, how do I explain this? Usually these tests look at differences in the mean compared to the amount of variation in the measurements to say, yes, they're different and their variation doesn't overlap. Therefore, we can say with some degree of certainty they're different. With velocity values, we only have one per set of releases. So it's not really enough data to compare beyond an eyeball. Does that answer your question?
Yeah, if you could put the slide up that shows your little, which ones you thought were significantly different, which ones you thought were